Okay, so welcome back, and now I'll start the discussion on unsupervised pre-training. So the main question is, right, what has changed now, right? What has happened in 2006 which has allowed us to train these deep neural networks, and why has deep learning become so popular? That's the main question so far, right? Uh, so we look at this seminal work in 2006 which made training deep neural networks more possible, right? So the original paper actually talks about something known as RBMs. We have not done RBMs yet, and we will not do it in this part of the course. I will try to explain it in the context of autoencoders. Again, we have not done autoencoders. Now I have also uh, uh, autoencoders will also not be a part of this course because we have replaced it by other more advanced optimization algorithms, as well as a discussion on transformers. So we did not have place to put in autoencoders given the number of lectures that we had. So but you could refer to my older lectures on autoencoders if you want, and whatever we need I'll anyways cover in the next few slides, right? So we have not had a detailed discussion on autoencoders, but I'll just quickly brush up on whatever I need in the next few slides, right? So 2 points here. One is the original paper talks in the context of RBMs. I'm going to talk about this idea in the context of autoencoders. We have not done autoencoders in this offering of the course, but I'll just quickly cover the concepts that are required. So now consider this deep neural network, right? It is like a 4-layer network plus the input and the output layer. And as I was saying before 2006, it was hard to train networks which are 4, 5, 6 layers and so on. Right? They did not converge well, right? Now let us focus on the first 2 layers, right? And what I'm trying to do is I'm going to try to explain the idea of unsupervised pre-training, right? So now I forget about training the entire network. So what is my input? That might be some x's that I have. Right, and this x belongs to some r n, so it's an n-dimensional input, and I have taken the simple case when I'm just trying to predict one output, right? So my y belongs to r, right? Now I'm not focusing on this entire, and I decided that I want to use like a very complex deep neural network as my function approximation. That this is the relation between y and x and y, right? And now I'm focusing on this first layer where I have the input and then the first hidden layer h1, right? Now what we do in unsupervised pre-training, or at least as it was introduced in this paper, now today unsupervised pre-training still exists, but in a much different form, which is conceptually similar, but with a lot of moving parts having changed, right? This is in the context of feed-forward neural networks. Today we typically talk about it in the context of transformers, and the loss functions have evolved. None of that matters at this point, but I'm just saying that when I'm talking about unsupervised pre-training right now, I'm talking in the context of this work in 2006, right? Okay, so what we will do is we will take x as the input, okay, and we'll focus on a very simple problem first, right? So this x is the input. I have just taken the first hidden layer, so I have taken the hidden layer as it is. And now instead of feeding this hidden layer to the next layer, I just disconnected the network, and what I have done is I am now trying to predict x again, right? So think of this way, that I had say some 1024 dimensional input, then I have a hidden layer in between which is say 256 dimensional, and then again an output layer which is 1024, and my goal is to do the following, right? First compute this 256 dimensional hidden representation, and then again reconstruct the output from it, right? And my goal would be that if I call this x hat and this as x, then since I'm reconstructing, my x hat should be as close to x, right? And that is what this loss function is calculating. So my x was n dimensional. So along each of these n dimensions, I want to reduce the error between the prediction and the construction, and I want to do this for all the m training examples, and I want to consider the average, right? So that's the objective function. This is clear. Now what am I trying to do here, right? What is happening here, right? So let's try to understand this conceptually. That suppose I'm able to do this. Suppose I'm able to train a network which is able to reconstruct x hat with 0 error. That means I am taking an x, I am doing a wx, right? That's a transformation I do. Then I pass it through a sigmoid function. I'm ignoring the biases, okay? So I get some hidden layer h1, right? And then from the hidden layer, I am reconstructing x hat as say w times h1, Okay, this is what I am doing in this network, right? My input layer, I am doing first a linear transformation followed by a non-linearity, and then whatever h1 I get, I just reconstructed the x hat from there. If you want, I can just add the bias also here, and I can add the bias here also, right? So if you want, that makes you more comfortable, then that is what it is, right? Now suppose I am able to do this in a way that I am able to reconstruct x hat from x perfectly. That means my error is 0. What does that tell you about h1? So it tells you that h1 actually captures all the information that was there in x, right? Because I have done a compression, I have gone from 1024 dimensions to 256. Now we know that in many applications our input has a lot of redundancy, right? So I would have captured weight, height and BMI. All three are not needed. From the weight and height I can know the BMI, right? Similarly, I would have captured several correlated things. I would have captured weight in weight in kilograms. Maybe I would have captured weight in pounds also, or weight in grams also. Similarly, height in centimeters. Because this data is flowing in from multiple channels, so I don't know. Even for example, I would have calculated the salary. I would have salary as one of the inputs, and I might also have the income tax as one of the inputs, right? Now these two are completely correlated. So in that case, I did not have both these inputs, right? So my data has a lot of redundancy. So I'm doing some sort of a compression where I'm reducing it to 256 values, and then I'm trying to reconstruct the input from these 256 values. So if I'm able to do this perfectly, that means this hidden layer that I had is capturing all the important characteristics of my input, right? And that is enough for me to reconstruct the input, right? That's what typically happens in compression. So that's exactly what I am trying to do here, and this is the idea in an autoencoder, right? I want to learn a more compact representation of the input, and the way I do it is that I use this bottleneck layer, right? And then I try to reconstruct the loss, and if I'm able to do this, then I have captured all the important information in this 1024 dimensional data by just using 256 dimensions, right? And we can show that under certain conditions, this is actually equivalent to principal component analysis, which is again a data dimensionality reduction technique, right? And the same thing you're doing here, you're reducing the dimensions of the input data, right? So that's all that we want to know about autoencoders. This is what an autoencoder tries to do, and this is what I'm trying to do here, right? So while doing so, I am actually ending up computing a abstract representation of the input in this layer, right? So this layer is now computing a good representation of the input. It's capturing all the vital characteristics of the input which are enough to reconstruct the input, right? So that is what is happening here, and this is the objective that I'm going to work with. Now notice that this is a single layer network, right? So I had a problem, I had difficulties in training a deep neural network, so I've ignored that problem. I've said, okay, I'll worry about that later. Right now, let me just focus on this, right? So if I am able to train this entire network, what does that mean? That this layer is producing good outputs, this layer is producing good outputs, this layer is producing good outputs, and this layer is producing good outputs, and finally the final output is good, right? So this entire problem was becoming difficult for me. I was not able to train the entire network. So I'm saying, let me just focus on one layer now. And for this layer, what is the definition of good? That it should capture all the characteristics of the input. That is how I have defined goodness, and I have designed this objective function accordingly, and I have reduced the problem to training a network containing just one hidden layer, so input, hidden and output, and this is a shallow network, and shallow network training was not a challenge, right? So I could train a shallow neural network, so I have reduced my problem to training a shallow neural network. Now how do I go from here again, because eventually I want to train the deep neural network? That is not clear now, but the first step is to just learn layer 1 effectively. Is that clear? No, this could be W1 and W2. Yeah, so when you compute the loss, you are using that, right? So x hat, you are computing the difference between x hat and x. So there you are using that information, right? What was my original input? So loss is defined in terms of what your original input was, right? So that is getting used there.
So dimension of x var and x will be different.
It will be the same.
It depends upon the input layers, right?
No, so this is n dimensional, and then you are reconstructing the n dimensional input.
Okay, from that.
Yeah, right? Yeah. Okay. So, so this is what we have done. Now, once we have understood this, we are just going to repeat this process again, right? And let's see what I mean by repeat this process again. Yeah, this is all written in words, whatever I had said. And yeah, and one important thing is, where is the word unsupervised coming in here, right? So remember that in this problem that I'm currently interested in solving, there is no y, there is no label here, hence it is in unsupervised. Right? I'm just having the inputs, and my loss function completely depends on the inputs. So I don't care, right? Even if you had not given me y, I don't care. So there is no label or supervision being used here, hence this is whatever I'm doing right now is unsupervised. Later on, of course, I will move to a supervised objective, but right now whatever I'm doing is unsupervised. Okay. Now once I have done this, I am going to repeat this process. So what I am going to do now is that I was happy that I had learned H1 well, right, from the previous training. So I did that round of training and I kept training till my training loss reduced and my H1 was a good representation. Now I am happy with H1, right. So now H1 is some, say, d-dimensional input. Now I am going to plug in H2, okay, and then again try to reconstruct H1 hat, right. And I'm not going to touch these parameters. So you can think of the entire training data that was given me, the M training samples that were given to me. For each of those training samples, I have computed H. Okay, I have done that. Sorry, H1. I have done that, right? Now my training data becomes H1. I pass it through a network, a layer called H2, right? So this was maybe d-dimensional. This could be d-dimensional or some d1 dimensional. And then I again try to reconstruct H1 from there. So it's the same training objective, right? So now remember that the H's, while we think of them as hidden layers or outputs, they are also the inputs to the next layer, right? So just as X is H0 and my first problem that I had solved was for H0, now I am solving the same problem for H1. Given an H1, I want to reconstruct it through a single layered network, right? So again, once again, I am training a shallow network, one input layer which is H1, which is fixed. I have computed all the H1s using the X that was given to me and the training that I had done in the first iteration. I had computed all the W's. I was happy with whatever W's I have computed, and using those W's, I have computed H1 now as W times X plus C or B, whatever we had used into that, right? So this computation I have done. Now I am thinking of H1s as my input, passing it through a hidden layer and then reconstructing H1 hat, and again using the same objective function with X replaced by H1, right? So nothing new that I'm doing. So again, I'm just training one layer at a time, right? This is the only layer that is getting trained, which means this is the only layer that I'm trying to reconstruct, right? And now what am I doing? I had said that H1 captures all the characteristics of X. Similarly, now H2 is capturing all the important information of H1. So it's yet another level of abstract representation of the original input, right? So this was already an abstract representation of the input which had discarded all the unimportant information and told you everything that you need to know about X, and I can fully reconstruct X from here. Now H2 is an abstract representation of H1 which kind of captures every information in H1 and it's enough to reconstruct H1 from there. So H1 is an abstract representation of X, and H2 in turn is an abstract representation of H1. So H2 is like a deeper abstract representation of X, right? So that's what you're doing, and that's what the idea in a feed-forward neural network is, right? Every layer captures a more and more abstract representation of the input, right? So now again you have focused on layer H2 and made sure that this computes good representations. That means you have ensured that these weights that are sitting here are now some good or well initialized weights, right? So that's what you have done. And now you will continue this process. In the next iteration, now you will freeze H1 and H2. Now H2 becomes your input, and now you will throw in H3, right? And then you will try to learn these weights such that from H3 you are able to reconstruct H2 perfectly, right? And you keep doing this till all the L layers that you have. So you are learning one layer at a time, and each layer is trying to learn some weights which are an abstract representation, which allow you to compute an abstract representation of the input, right? So now this is what you are going to do. So at the end, right, what have we achieved? That all our layers have been trained to compute a better representation of the input, right? And now I return back to my original problem. My original problem was that I was given some X and some Y, right? And I wanted to learn the relation between them, and this was what my fx is. Now individual components, and fx was itself a composite function, right? I was first computing this, then passing it, then computing this, and so on. So all these individual components of f of x now I have learned well, right? So whatever weights I learned in those individual pre-training steps, I'll just retain those. I'll start from there. I'll not start from random initialization. I'll start from those, right? And I'll plug in these weights randomly because these weights I did not learn. So I'll plug in these weights randomly. And now I'll go back to my original training objective, which depended on y hat and f of x, right? Or yeah, sorry, not y hat, y and f of x, right? Or this is what my objective function was. So now I'll train for this objective function. And when I'm doing this, I will of course update these weights. I'll do the full back propagation. I'll update these weights. I'll update all of these weights, right? But when I'm updating these weights, remember that I have not randomly initialized them. I have started from whatever my best configuration was while doing those individual unsupervised pre-training, right? So this is what I have done. Now why does this work? What is the implication? All of that we'll discuss, right? But we have understood the procedure that we are training one layer at a time. It's unsupervised because we are not using the final label. Once we have done the full unsupervised pre-training, we plug in the supervised objective and we train for that supervised objective. So I can think of this as L of omega, right? This is what my L of omega is, right? So this is what was the unsupervised training objective, and when they did this, they showed that it's possible to now train the entire deep neural network effectively, a thing which was difficult earlier, and they trained quite a few, quite a bit deep neural network. I have shown still in modern terms this is still a shallow network, but they trained quite a bit of a deep neural network, right? So what have we done, right? So in effect what we have done is we have initialized the weights of the network using that greedy unsupervised objective, right? Where why am I calling it greedy? Because at every layer I did not care about what is happening in the other layers. I just wanted to make sure that that layer is trained properly. That's why it was greedy and it was unsupervised. And whatever was the result of that greedy unsupervised training, that is the initialization that exists in my network, right? So now why does this work better is the question. And I'll give you two options. Is it due to better optimization, or is it due to better regularization, right? Now the first thing that I want to ask is whether you understand the difference between these two questions. So what do we mean by optimization? Optimization deals with dash data, training data or test data? Training data. So when you are doing optimization, when you are minimizing the loss function, right? Remember that you are taking the average, whatever is your loss function, over, you're computing with respect to some yi and f hat of xi, right? And this loss function depends on the training data. These xi's and yi's are your training data. So optimization, you only have access to training data, you don't have access to test data. But during regularization, what do you mean by regularization? Regularization is used for better generalization. So when you say better generalization, it means that of course I know you will do well on the training data, you will be able to drive the error to zero. But what I care about is generalization, which means on test data your performance should be better, right? So what is happening here? Is it that if we did not do unsupervised pre-training, you are not able to do better optimization itself? That means even for the training data, for which I have been assuming in all our discussions, hey, training data we can easily drive to zero, we just improve the complexity of the model and we can drive it to zero. But before 2006, is it that even on the training data I was not able to drive the error to zero? Or was it that because of unsupervised pre-training, I was able to get better performance on the test data, right? So which of these is the reason for it to work better? Was it acting as a regularizer or was it acting as a better optimizer, right? So now a comment that I want to make here, right? So this is, I'm talking about the work which happened in the period of 2006 to 2009, right? So this work 2006 happened, this unsupervised pre-training idea came out, everyone was excited that now we can train deep neural networks. And then people started inspecting, right? Why is this working? Is it optimization, regularization, and so on? And not many clear answers emerged there, right? But what got reinforced that, hey, indeed something is happening and now it is possible to train the deep neural networks, and it could be because of optimization, it could be because of regularization. So why don't we design better methods of optimization? Why don't we design better methods of regularization and so on? And that's the effect that we saw from 2009 onwards. 2011-12 onwards, we saw a series of better optimization algorithms, right? We saw all of that converging into Adam and then Nadam and then again a few variants of that, right? So this sparked interest. So whatever happened in this period, maybe people did not have correct answers because these were again early days, but these investigations suggested that hey, maybe there is merit in going after better optimization algorithms. Hey, maybe there is better merit in going after better regularization methods. And we saw that one of the regularization methods that came out drop out around 2012 to 2014, that is still very popular, right? So because of these investigations, people got excited and said, okay, it could be because of optimization, it could be because of regularization. If that is the case, then maybe unsupervised pre-training is not the only method which leads to better optimization. I could come up with better optimizers. Or maybe unsupervised pre-training is not the only method which leads to better regularization. I could come up with better regularizers. Then early stopping came, dropout came, and all of these, right? So then all of these got used in the context of deep neural networks. And then people also thought maybe there are other things. Maybe you could initialize the weights better because looks like unsupervised pre-training is doing some kind of initialization of the weights. So why don't I come up with better initialization methods? Then people said, okay, maybe there is something to do with activation functions because we're talking about gradients and maybe something happens and if we change the activation functions, we might get better gradients and maybe things would improve, right? So all of that, whatever work happened in this 2006 to 2009 period, which I'm going to talk about for the next 15-20 minutes, none of this I will be able to give you very conclusive answers. Hey, it was definitely due to optimization or definitely due to regularization, but that does not matter. What matters is it opened up these possibilities, and following this work, we saw a lot of other advances, half of which we have already seen. We have seen regularization methods, we have seen optimization methods, and today we are going to see the remaining half of this once I go over this period of 2006 to 2009. Okay, so these are the two possibilities. We don't know what it was, and I'll show you some works which hinted at both of these, and then from there on, we'll continue the discussion.